Gravity and electromagnetism share some common similarities. For instance, they are both mediated by massless fields and therefore lead to potential in 1/r. They also exhibit some differences, like the fact that two charges of the same sign repel each other while two masses attract each other. We already have an indication that this has to do with the spin of the field which is mediating the interaction. And we also saw that because there is a field mediating the interaction, we can have excitation of the field, disturbance of the field which propagates on mass shell, and therefore we have a particle associated to this field. In the case of electromagnetism, this is a photon. In the case of gravitation, this is a hypothetical graviton. So let's see if we can find some qualitative arguments without proof, which will tell us what the spin of the graviton can be. First, we need to ask ourselves, how do we know that the photon has spin 1? Indeed, it is not straightforward to measure directly the spin of a photon. However, we know what type of sources couple to the electromagnetic field, and in particular we know how they transform under Lorentz transformation. So the time-like component of the source which couples to an electromagnetic field is a charge density ρ, and its space-like component is the current density J. So we can find, for instance, an inertial frame where a charge is at rest, but that's not a scalar. That's not something which is invariant under Lorentz transformation, because, for instance, if I boost the system, if I boost the charge, then I see it moving. If it moves, it has a current. So clearly the charge, electric charge, doesn't transform as a scalar, but transform as Lorentz 4 vector. Then when I build an action with a source coupling to the field, I need to have a Lorentz scalar. Therefore, the only possibility is for the field to also be a Lorentz vector and therefore to carry a spin 1. In the case of gravitation, we haven't found the graviton yet, and of course it's not in the near future that we will be able to measure its spin. However, we have a classical field theory for gravitation, which is general relativity. And in general relativity, what plays the role of a source is the stress-energy tensor. And more precisely, it's a ranked 2 symmetric tensor. So the action being a scalar, the field must also carry two Lorentz indices and therefore be a rank 2 tensor. In fact, in general relativity, the field is related to the metric itself, because the stress-energy tensor is acting on spacetime by inducing curvature in spacetime. In addition, the field is also a symmetric tensor. Indeed, we could always decompose rank 2 tensor into a symmetric and an asymmetric component, but if it was asymmetric, if we only take the asymmetric component of the field, in the last step I use the fact that nu and mu are dummy variables, therefore I could change mu into nu and nu into mu. And when something is equal to minus itself, then it has to be 0. Therefore the field phi has to be a symmetric rank 2 tensor. So in a matrix form, phi will be a 4x4 matrix, but with only 10 independent elements. So a symmetric rank 2 tensor is able to encode 10 degrees of freedom, in the same way that a 4 vector is able to encode 4 degrees of freedom. But by constraining the derivative of the field, and that is by fixing the gauge, we were able to reduce this number to only 3 degrees of freedom, therefore corresponding to a spin 1 field. Similarly, if we constrain the derivatives of the rank 2 tensor field, we reduce the number of degrees of freedom by 4 because we have 4 constraints. And we can add one more constraint by imposing the product of the Minkowski metric times the rank 2 tensor field to be equal to 0, where I wrote eta the Minkowski metric because in general relativity G mu nu usually refers to the curved spacetime metric. So we end up with 10 minus 4 minus 1 degrees of freedom, so that's 5 degrees of freedom. And that's exactly what I will need to encode the degrees of freedom for a spin 2 field. So that's why we think the graviton, if it exists, should have a spin 2. Of course, this discussion is only qualitative. I didn't prove anything. Nevertheless, I already knew that the graviton could not have a spin 1, otherwise two masses will repel like they do for two charges of the same sign. Finally, as a last comment, you probably know that there is no quantum field theory for gravity, and that has to do with the fact that the graviton has a spin 2. Indeed, when we want to calculate physical quantities from a quantum field theory, we need to make sure that they are finite, that there is no divergence. The problem is we often have to deal with a lot of divergence and quantities which goes to infinity in quantum field theory. And one way to deal with that is to use what we call renormalization. So we are not going to talk about renormalization. This is an advanced topic for quantum field theory. However, you just keep in mind that a theory to be physically meaningful in quantum field theory has to be renormalizable. And it turns out that theories with spin greater than 3/2 are not renormalizable. Therefore, there is no way we can build a quantum field theory with gravity using a graviton of spin 2, which will be renormalizable and which will then lead to meaningful physical quantities. For this reason, we believe that quantum field theory can only lead to effective theories, and that is, they are only an approximation to more fundamental theories. For instance, this could be string theory or other candidates for quantum gravity.